X of tau is an exponentially decaying signal, and it looks something like this. Then your h of tau. See, here in this integral, tau is the independent variable. Tau is the independent variable. So we are writing x of t as x of tau. We are just changing the independent variable from t to tau. And similarly, so we have got x of tau in this integral. And we need to get h of t minus tau. Okay? H of t minus tau is obtained by reflecting h of tau about origin. That meaning we will be getting h of minus tau first, and then shifting it to right we'll see that, like, and shifting it to right by 2 t units if t is greater than 0, or to the left by mod t units if t is less than 0. Yeah, so you first note down this, then we'll quickly discuss what does this mean. So we got x of tau here. So this is x of tau, and we need to now get h of t minus tau. So how do we get h of t minus tau? We will first plot h of tau and then reflect it about tau is equal to 0 to get h of minus tau. So let me show you. H of tau is this 1, and let me say this is h of tau, because h of tau is a unit step function. Unit step function is 1 only from only when the independent variable is greater than 0, and it is 0 for the negative values of independent variable. So here the independent variable is tau. Okay, now we got h of tau, and we need to get h of minus tau. H of minus tau is what? We need to reflect this signal about origin. So this is h of minus tau. So this signal is towards the right, from origin. From origin it is going to the right, and when I reflect it, it's like mirror reflection. It becomes a left-sided signal. It is right-sided signal here. When I reflect it, it becomes left-sided signal here. So now I got h of minus tau. But what do we want? H of t minus tau, right? So we want h of t minus tau. H of t minus tau, we are writing that as h of minus tau plus t, right? This is also correct, right? H of minus tau plus t. So now to obtain h of t minus tau, we need to shift the signal to the right. Shift it to the right by t units if t is a positive number, or shift the signal to the left by by modulus of t units if t is a negative number. So let's see that in the next page. Right? Okay, you understood. So we are trying to evaluate we are trying to compute this integral, meaning we are trying to obtain the output signal, and for that we need this product x of tau into h of t minus tau. So we plotted x of tau because we know what is x of t. So simply replacing t by tau will give you the x of tau. Now we want to obtain what is h of t minus tau. So how are we getting h of t minus tau? We are first plotting h of tau because we have h of t. From h of t, by replacing t with tau, we got h of tau. Now from that we are getting h of minus tau just by reflecting the signal about the origin, about tau equal to 0. So we are getting h of minus tau, but we want h of t minus tau. So that meaning now we are trying to get h of t minus tau by shifting it to the right or left. Now I'll for better understanding, I'll be plotting these things again here, just for a quick understanding. So this is 1 and this is x of tau, this is tau, this is 0. And this is tau, and I'm just plotting directly the h of minus tau. H of minus tau is so this is 1. This amplitude is 1 and it goes up to infinity. It goes up to infinity like this. Now what we need to plot is h of t minus tau. H of t minus tau. We are trying to plot for t less than 0. For t less than 0. So for t less than 0, we have to move this signal to the left, right? So this is t. So h of t minus tau, for t less than 0, it moves to the left. And for sorry for this. So and again for h of t minus tau, for t greater than 0, it would be something like this. So this is t and this value is 1. Yep. So for t greater than 0, we are moving this signal to the right by t units, and for t less than 0, we are moving this signal to the left by t units, right? Okay. Now we when we let me write this, y of t is equal to minus infinity to plus infinity x of tau h of t minus tau t. Sorry, it's not dt, it's t tau. So let us see this. Let us examine this product. Product of these two signals, x of tau, h of t minus tau. Okay. For t less than 0, what happens? That meaning we are trying to multiply this signal. We are trying to multiply this signal with this signal. For t less than 0, we are trying to multiplying this x of tau with h of t minus tau. And you can see that h of t minus tau is non-zero only on the negative side, whereas x of tau is non-zero only on the positive side, right? For so the product of these two signals, so the product of that this signal is 0, right? For t less than 0, x of tau into h of t minus tau is 0. This is the geometric way of doing convolution. So a geometric interpretation of convolution is very, very important, because just solving this by this form, like you can also solve this just by algebraic manipulations, by solving these equations, but having geometric understanding will help you in solving these problems simply. Sometimes the math becomes too much if you don't visualize the signals. Uh, okay, now, so that meaning for t less than 0, this product becomes 0, and when the product becomes 0, that implies y of t is also 0 for t less than 0. Now for t greater than 0, now look at product of this signal with this signal, right? So product of these two signals, what happens? So this signal is existing from 0 to infinity, whereas this signal on the positive side, it's non-zero from 0 to t only, right? So x of tau into h of t minus tau, so this is equal to e power minus a tau, is e power minus a tau for tau varying between 0 to t and is 0 elsewhere, right? See, when you consider for t greater than 0, h of t minus tau is this signal, h of t minus tau is this signal, and x of tau is this signal, and when we multiply this with this, what you get is only in this portion you will get non-zero signal, because after this portion h of t minus tau is 0, and in the left half plane x of tau is 0. So this product of this signal x of tau with h of t minus tau, right, is non-zero only for this. So that means y of tau equal to, for t less than 0, y of tau equal to 0 to t e power minus a tau d tau, that is equal to minus 1 by a e power minus a tau 0 to t, that equal to e power minus at by a. So for t greater than 0, y of t is this, and for t less than 0, y of t equal to 0, So I hope you understood. Like if there are any questions, let me know. This geometric interpretation is very, very important. It's not only for your exams, but wherever you go, like whether when you become a core engineer, when you work in electronics and communication industry, either as a communications engineer or signal processing engineer or even a VLSI engineer, where you do deal with signals and mainly the signals and LTI systems, you have to be having this intuition. It's not only for your exams or for scoring marks. It helps you everywhere throughout life. Like when you work, if you work in your core area, like any of these ECE related jobs, if you work. Uh, so so finally, what is the solution for this? So y of t is equal to 1 minus e power minus at by a for t greater than 0, that is 0 for t less than 0. See, the same thing I can write in a much more compact manner as y of t equal to 1 minus e power minus at by a into u of t. See, these two things are equal, right? Because u of t is non-zero, u of t is equal to 1 for t greater than 0. So instead of writing like this, I can write this is equivalent to this. Fine. So let me put this slide just for 1 minute. If any of you have any difficulty or any misunderstanding or any confusion about this, you can ask me. Right? Yep. So now let's take another example. So this is example 2.7 from the textbook Oppenheim and Wilsky. So here x of t is, what is this, x of t here? Yeah, this is another simple example. X of t is a rectangular pulse, is 1 0 for, sorry, 0 less than t, yeah, okay, so let's plot this. Okay, we'll plot it later. And h of t is t for 0 to 2t, and it's 0 and it's 0 otherwise. Right? So while I plot these signals, you can also plot without looking at the screen, right? So now we have to obtain y of t equal to minus infinity to plus infinity, x of tau, h of t minus tau, d tau. So we need to find the product x of tau into h of t minus tau, and then we have to integrate that product from minus infinity to plus infinity. Then we'll get y of t. So it's equal to what? So this is a question. So now we have to get, as we did in the previous example, x of tau. So let me put this as tau and x of tau, and what did this equation say? X of, so simply replace this t with tau, you will get x of tau. So it is 1 from 0 to t, and is 0 elsewhere, right? Now what is h of, so we need to get h of t minus tau. How do we get h of t minus tau? We will first plot h of tau, we will reflect it about the origin. So uh, so this is 2t, this is 0, and this is h of tau, because between 0 to 2t it is simply t. T is a uh, t is a straight line having slope 45 degrees, right? This is a 45 degrees line angle, so h of tau is tau. Now what do we need to get? We need to reflect this, right? So h of minus tau, how do we get? So this is minus 2t, this is 0, so this is h of minus tau. We are simply reflecting this about the origin. So this again a line with slope 45 degrees, right? And then for and then we have to shift this to the left by t units or to the right by t units, depending on whether your small t is positive or not. If it is positive, we have to shift it to the right by t units. If it is negative, we have to shift it to the left by modulus of t units, right? And then multiply these two signals. So okay, so now let's again examine. Now h of minus tau is this, and for t less than 0, it still moves to the left. Okay, first you note down this. I think you are following it up. Like I'm not. I'm going very slow, as you can see that, right? Yeah. Okay. Now let me go to the previous page. Sorry, this pen is changing its. There is some problem with this. For t less than 0, the product h of tau, x of tau, h of t minus tau is equal to 0, because I'm just quickly drawing that again. This is x of tau, this is 0, this is t, and this is 1. This is tau. Sorry, just wait. I need to draw it correctly. So this is t, this is t minus 2t. This is for t less than 0. This is h of t minus tau. This, right? So for if it is left hand side, the product of these two signals is 0. That's what I'm saying. For any amount t less than 0, the product of these two becomes 0. Right. So if for t greater than 0, it will move to the right. So this will be t, and this will be t minus 2t. This is 0. This is h of t minus tau, and this is for t greater than 0, and this is for t less than 0. Okay. So when it is on the positive side, when t is greater than 0, this is moving to the right. When this is moving to the right, this overlaps partly with x of tau, and there will be some signal. But when it moves to t here, right? So well, let me write one more thing here. So this will be when t is greater than when t equal to 3t. So this is t. So this is 3t. This x of t minus tau. This tau. So for t equal to 3t, this signal will have moved to the right, and it will be from t to 3t. So but this signal is only from 0 to t. So for t greater than or equal to 3t, right? Again the product x of tau, h of t minus tau is 0, because when we are shifting this triangular signal to the right, When you shift it by some amount, it's okay. These x of tau and h of t minus tau still overlap. But if I shift it by 3t units, then the signal has shifted like this, and x of t is only up to this. So x of t lies only this. So from 3t onwards, again there is no overlap between x of tau and h of t minus tau, right? So y of t is 0 for t less than 0 and t greater than or equal to 3t, right? So y of t is non-zero only between 0 to 3t. Y of t is non-zero only for values right. Now I'm leaving this. Yeah, so we have shown that y of t is 0 for t less than 0 and y of t is 0 for t greater than or equal to 3t, and in between 0 to 3t you will have some y of t, and you can solve that y of t. See, you have to shift this from time to time and then evaluate this product and then integrate it. So you can do this example as a homework problem. So we have solved most of this problem. Like we have determined that it is 0 for t less than 0, it is 0 for t greater than or equal to 3t, and only in this interval you have to obtain the product of this triangular signal with this rectangular signal and then integrate that. And for solution you can look example 2.7 in Oppenheim and Wilsky book, right? So at least you can do this example, or maybe you can solve this right now if you want 5 minutes, but it takes about more than 5 minutes. It takes minimum 10 minutes for you to solve this, right? Okay. So we'll do so in these two examples. What we did was we have taken signals such that the convolution is 0 for some parts, like the convolution is 0 for some values of t, for some values of the variable t, right? So that's how it is somewhat easy for us to do this. So now next let us take one more example where the convolution is not 0 for any value of t, right? So the convolution is not 0 for any value of t. So let's go to another example, the last example in this class. So this example is also from Oppenheim and Wilsky. So x of t is equal to e power 2t u of minus t, and h of t equal to u of t minus t, right? So again the problem is the same. What is y of t? Now so as we did previously, let's first plot x of tau, then let's plot h of t minus tau, and let's determine the product x of tau into h of t minus tau, and then evaluate it, and then integrate it. So what do we get it here? Okay, so we are trying to plot x of tau. See, x of t is e power 2t u of minus t multiplied by e. See, e power 2t is something like this. It is 1 at t equal to 0, or e power 2 tau this is. So this e power 2 tau, and this is being multiplied with u of minus t or u of minus tau here. So u of minus tau is non-zero only in this interval. So this part becomes 0, right? So this is e power 2 tau, u of minus tau is this. This is an exponential signal. Now u of t minus 3. So I want to plot h of tau. So h of tau is something like this. So this is tau equal to 3. Right? This is simply a unit step function shifted to the right by 3 units. Is simply a unit step function shifted to the right by 3 units because this u of t minus 3. And then it is, I have to reflect this. So this h of minus tau, how do I obtain? This is equal to minus 3. So this h of minus tau, and now I want to obtain h of t minus tau. So h of t minus tau will be simply, it will be this signal shifted to the left or to the right. So this value is t minus 3. This value is 0. Yep. Now you see, if t minus 3 is less than or equal to 0, okay, so depending on the value of t, this t minus 3 changes. So if depending on value of t, this entire signal is either moves to the right or to the left, right? This unit step function is moving either to the left or to the right. So and its starting point is t minus 3. If t minus 3 is less than or equal to 0, so for example, if t minus 3 equal to 0, the signal will be from 0 to minus infinity, and that we need to multiply with this. So when t minus 3 is less than or equal to 0, then x of tau into h of t minus tau is equal to e power 2 tau for minus infinity to tau to 0. Oh, no, to t minus 3. It's up to t minus 3. Yeah, sorry. For t minus 3 less than or equal to 0, the product is non-zero for equal, yeah. And it's 0. And it's 0 otherwise. Now, if t minus 3 is greater than or equal to 0, so when t minus 3 goes to the right, so let me draw that picture. So this is for t minus 3 greater than or equal to 0. H of t minus tau, this is tau. So in that case, then the product of x of tau with h of t minus tau is non-zero only from minus infinity to 0. Then x of tau into h of t minus tau is equal to e power 2t for minus infinity tau less than or equal to 0, and it's 0 otherwise. Okay, so I don't know whether you are getting what I'm saying or not, like, but I'm just trying to split this up into different portions so that you can evaluate this easily. You just have to look at shifting this h of t minus tau here and there, and then accordingly you will understand all these things. Once you visualize shifting this h of t minus tau to the left and to the right, then everything follows easily. Only you need that imagination, or you can plot multiple such diagrams in your notes and then try to understand. Right? Even in the exam, the more diagrams you write, then the examiner will also understand that you are what you are trying to do. Right? Okay. So now now only we need to what we need to do is, so this meaning, see here we said t minus 3 less than or equal to 0. That means t less than or equal to 3. In this case, t is greater than or equal to 3. See, when I said t minus 3 less than or equal to 0, that means t less than or equal to 3. When I said t minus 3 greater than or equal to 0, that means t greater than or equal to 3. Right? So, y of t equal to minus infinity to t minus 3 e power 2 tau t tau for t less than or equal to 3, and this is equal to minus infinity to plus infinity, sorry, minus infinity to 0, e power 2 tau d tau for t greater than or equal to 3. So how do you find y of t now? For t less than or equal to 3, you will integrate this from minus infinity to t minus 3, because it is non-zero only for the period minus infinity to t minus 3, and for t greater than 3, you will integrate this from only 0 minus infinity to 0. So this is something for t less than or equal to 3, and this is something for t greater than or equal to 3. So you fill this some things as homework. Okay, similarly this is example 2.8 from Oppenheim and Wilsky book. So this is example 2.8 from Oppenheim and Wilsky book. You can solve these two things easily, but just to check your answers, you can look at this textbook, which must be available, second edition of Oppenheim and Wilsky, and I'm sure all of your college libraries will have this book. This is one of the very standard book on this signals and systems. Right. So we are done with all the three examples, and then we'll move on to the properties, discuss properties of linear time invariant systems. Right. So I just want to take a quick break. Okay. So that's all for the examples. We can solve more problems, but like, yeah, if you have any specific things, we can solve, but otherwise we can. We'll be starting with the next topic. Yeah, so the first thing to note is an LTI system is completely characterized by its impulse response. Uh, is completely characterized. That what does it mean by its impulse response? It means that if somebody says their system is an LTI system, linear time invariant system, and if they give you the impulse response, that means you know everything about the system. If you know the impulse response of an LTI system, that means you know everything about the system. So, and okay, so one thing for you to remember is we are considering only linear and time invariant systems here. We are not considering non-linear systems. We are not considering time variant systems, right? So, and the notation for this is if h of t is the impulse response. What is impulse response? The response produced by the system when a unit impulse is the input, right? So if you give delta of t as the input to the system, and if the system produces an output h of t, then h of t is called the impulse response of the system. If h of t is the impulse response of an LTI system, we denote it by something like this. So this this box, rectangular box, is the system, and generally we denote input by, okay, maybe I should write here as input signal, and here comes output signal. So now let's get back to the commutative property. So it says that if you commute x of t with h of t, that is equivalent to, if you convolve x of t with h of t or convolve h of t with x of t, both are same. So this shows that minus infinity to plus infinity x of tau h of t minus tau d tau is left hand side. So right hand side it is minus infinity to plus infinity h of tau x of t minus tau d tau. Meaning either if I solve this integral or if I solve this integral, the answer will be same. The answer will be the same for both the integrals. So if I convolve x of t with h of t or h of t with x of t, both will be the same. Right? This is commutative, like, so you know that matrix multiplication does not follow commutative property, right? Just I'm just randomly picking up one example. That's it, right? Okay. But here the convolution follows commutative property. So proof. How do we prove that this integral x of tau h of t minus tau d tau we need to prove this integral is equivalent to minus infinity to plus infinity h of tau x of yeah, so yeah, maybe let's not write the final. So how do you prove? Simply by change of variables. Put t minus tau is equal to theta, which implies that tau is equal to theta minus t. Sorry, not tau is equal to t minus theta, and d tau is equal to minus d theta. So that meaning this will be plus infinity to minus infinity x of t minus theta h of theta minus d theta. So this I can write this as, I have to get rid of this minus d theta, so I'll interchange this plus infinity plus infinity, and this is h of theta x of t minus theta d theta. So this is nothing but convolving x of t with x of t. So convolving x of t with h of t is equal to this, and that equal to this. So that involves x of t convolve with h of t equal to h of t convolve with x of t. So all this we did by a change of variable. Simply by doing change of variable, we were able to prove this, right? This is a very simple proof, right? See this here, the variable tau is a dummy variable. The variable tau is a dummy variable. Similarly, here the dummy variable is theta. Instead of tau, you are simply putting some other thing as like you should be knowing about this dummy variable and like, right? You must have done many integral. You must have done many problems on integrals in your first year course, first year and second year math courses. Okay, so what is an important implication of this property? Implication of this property is if there is x of t and if I give that to h of t, a system, if I get y of t, right? If I give x of t as the input to a linear time invariant system having its impulse response equal to h of t, then let us say the output is y of t, right? Then what here y of t is x of t convolved with x of h of t. But what I can also do is I can give h of t as the input to a linear impulse to a linear time invariant system having its impulse response as x of t, and I'll still get y of t. You understood this? So you have a linear time invariant system with impulse response h of t, and you have an input signal x of t, and you have given this input signal x of t to the LTI system, and you got an output y of t. You will get the same output y of t, right? You get the same output y of t if you give h of t as the input to an LTI system with x of t as the impulse response, right? So you can interchange the input and the impulse response, and still you get the same output. Then next property is distributive property. It says that x of t convolved with h1 of t convolved with h2 of t is equivalent to x of t convolved with h1 of t convolved with h2 of t. This means that, say here you are first convolving h1 of t with h2 of t, and then convolving this result with x of t. Whether you do that or you first convolve x of t with h1 of t and then convolve with h2 of t, both are same. So if you are asked to convolve, if you are asked to find y of t, y of t equal to say h1 of t, h2 of t, then you can do the convolutions in any order you want. Meaning you have to solve this, say you have to solve this convolution of 3 signals, right? So think that you have to obtain the convolution of x of t with h1 of t with h2 of t. Then you can first convolve these two and then convolve this result with again this result, or you can convolve h1 of t. So you can first obtain the convolution of these two and then convolve this with this. It doesn't matter, both will give you the same result, right? So another way of, okay, what is its implication? What is the implication of this property? Means how can we use this property in practice? One of the most useful things about this property is, if there is a signal, if there is a system, something like this, okay, okay, no, oh, okay, see. It is not distributive property. It is associative property. Sorry, yeah. See, distributive property is something totally different, right? Distributive property is A into B plus C is equal to AB plus AC, right? Whereas associative property is A into B into C is A into B multiplied by C, or A multiplied by B into C. Yeah, so I'm very sorry, I just got messed up. So this is not distributive property. Simply you have to change the title. This is the associative property. What was the previous property we did? It was commutative property. Okay, yeah. So please, some of you might have noticed it, right? Like some of you following the clause carefully must have got this doubt that it is not distributive but it is associative. Okay, so anyway, this is associative property. Okay, so there is, like, for associative property, one of the main implication is this. say how do you do this? It does not matter which order you convolve. Huh. So that meaning, say if you are giving x of t as the input, then this is h1 of t, and if its output you are giving it to h2 of t, and then you are getting y of t, right? So now what is y of t? Y of t is x of t convolved with h1 of t. So here what do you get? You get x of t convolved with h1 of t, and this signal is the input to the next linear time invariant system having its impulse response h2 of t. So its y of t is, this is the input signal, and that is being convolved with h2 of t, right? But we are saying that this is also equivalent to h of t convolved with h1 of t, h2 of t. So this is nothing but you are giving x of t as the input to a system having its impulse response as h1 of t convolved with h2 of t, right? Have you understood this? So if there is a cascade of two linear time invariant systems, so we have got one LTI system having its impulse response as h1 of t, and we have got another another LTI system having its impulse response as h2 of t, and when we are cascading this, that is equivalent to having one LTI system having its impulse response as h1 of t convolved with h2 of t, right? So see, it is simply we applied this property again, h1 of t convolved with h2 of t is equal to, so this means that if we cascade two systems, this is equivalent to one system having its impulse response as so here is the input, here is the output, and here is the input, and here is the output, right? Now let's do the distributive property. this okay. So the associative property tells us that if you have many systems connected in series, many LTI systems connected in series, H1 of t, H2 of 3, H2 of t, H3 of t, and so on, then it can be replaced with a single system having its impulse response as convolution of the impulse responses of all the individual systems. Right? In other words, I just want to write that say H1 of t, H2 of t, and say Hn of t. This is exactly equivalent to a single system having H1 of t convolved with H2 of t convolved with and so on convolved with Hn of t. So both are exactly the same. This chain of systems can be replaced with one single system having its impulse response is equivalent to convolution of all the previous impulse responses. This is due to the associative property. Next, let's do the distributive property. So let's do this. So the distributive property is x of t convolved with h1 of t plus x2 of t. So the distributive property says that convolution operator is distributive over addition. This is equal to x of t convolved with h1 of t plus x of t convolved with h2 of t. Right? Okay. So this is a simple distributive property, and then let us see its application. What is its application? So let's consider this system. You have an input x of t that you are giving it to a system h1 of t. And you are getting an output y1 of t, and you are giving the same input to another LTI system h2 of t, and here you are getting an output y2 of t. And finally you are summing these two outputs y1 of t and y2 of t to get y1 of t plus y2 of t. Right? So can we simplify this system? So here you can see that this is connecting two LTI systems in parallel. Here this LTI systems h1 of t and H2 of t are connected in parallel, whereas in the previous example we have connected them in series. So now let us see. So y1 of t is x of t convolved with h1 of t, and y2 of t is x of t convolved with h2 of t. So our y of t signal is x of t convolved with h1 of t plus x of t convolved with h2 of t. Now using the distributive property, what we can do, y of t can be written as x of t convolved with h1 of t plus h2 of t. That's what we have written here, right? This x of t convolved with h1 of t plus x of t convolved with h2 of t is equivalent to x of t convolved with h1 of t plus h2 of t. Right? So that meaning we can give this x of t as the input to a single LTI system having its impulse response equivalent to h1 of t plus h2 of t. So that means we can give this x of t h1 of t plus h2 of t is y of t. So a parallel connection of two LTI systems can be simplified and it can be replaced with another LTI system having its impulse response is equivalent to summation of these two impulse responses. Right? Okay. So the three main properties are done, and then okay. So let me do one thing. You can do it right now in the class. Using the properties that we discussed in today's class. So there is a question something like this, like we have cascaded, the first system has got impulse response h1 of t, the second system has got impulse response h2 of t. Is it equivalent or not to the system So I'm trying to claim that h1 of t followed by h2 of t is equivalent to a single system having its impulse response h2 of t convolved with h1 of t. So is it, can I write it to be this equality sign? Can I write it here or not? And you have to justify this. You can read right now, and then you can do it right now before leaving the class, right? So we still have some 4 minutes, no, just 2 minutes left. So you can solve this and then leave. And then if you have any questions, you can ask me.